So my name's Tim Cooper, and I'm going to be talking to you about some tips and tricks in Unity. Now, some of the things I'm going to be talking about, I hope you already know, and if you don't, then you should definitely be considering them and using them in your projects. So who am I? I'm a developer at Unity. I'm technically on the editor team, but I'm responsible for a lot of other things outside the scope. So for example, I'm working with Michael and Philip on the new GUI, and I also have done quite a few graphics features within the engine. Before working at Unity, I used to make games. BioShock 1 and 2 are some of the ones that I've worked on. And on those projects, I was a technical developer working on optimizations for PlayStation and Xbox, as well as tools for users, for the developers of the games. So this is the list of topics I'm going to be going over today. It's going to start with just some simple rules and tips, like things like don't use find object, which is something that I hope you never use. Things like smart data structure layouts for reusability and much nicer serialization. Better ways to use serialized properties and property drawers. And then I'm going to go through a few things like memory debugging and graphics debugging, so that when you're making your game and about to ship it, or as you're developing it, you can know exactly what you're doing and keep things nice and small and very fast. And at the very end, I'm actually going to give you a sneak peek at one or two new features that will be coming during 4.x. They're mostly features that are associated with the GUI, but are not the GUI themselves. And you would have seen them in the keynote a little bit, but we didn't really talk about them. So what is the purpose of this talk? So in Unity, there are lots of little things that are good to know. And unless you've worked with Unity for a long time, they're very hard to figure out by yourself. So what I'm going to be doing is taking some lessons I've learned from looking at a lot of user projects. A lot of the time, I get emailed projects from users and asked to look at, and they ask, why is my memory bad, or why is my graphics performance bad? And a lot of the bugs we get are actually related to this. And more often than not, we find that these issues can actually be debugged at a user level if you have the right tools and understanding of how Unity works. So I'm going to hopefully impart some of that knowledge onto you today. And hopefully this will lead to you using Unity in a better way, and you'll enjoy the experience more as well. So the first thing I'm going to talk about is find object. Now, there are different types of find object in Unity. Say, you can find components in children. You can just search the scene for an object by name or by tag. And the problem with this is it's actually a very, very slow operation, and it doesn't scale with your scene. So to figure out the objects to return, Unity actually has to parse every object in the scene. So as your scenes get bigger, the slower this operation gets. So I'm going to show you a quick example of this. So here we have a profile of using find objects. So we have this some game object logic here. And internally, you can see this does use find object, which I'll show you in a moment. But it spends 3.48 milliseconds every time this function's called. And you can see on the performance debugger here, the spikes, which is every time this is executed. So let's go and have a quick look at this. So we have this scene called find object. And in there, we just have a scene. It has actually a whole lot of game objects in here. So the scene size is relatively what you'd expect in the number of game objects, which is what limits this in the real world. And let's have a look at what happens. So we have this functionality here, which has some game logic, and we have an update function. And every time we press space, we search through to find the towers in the scene, and then call the doAction function. I'll actually make this a little bit bigger so it's easier to see. Now, this is all well and good, and it actually works. But unfortunately, what you'll see is as we execute it, we will actually have spikes in the profiler. So we're now running. So every time hang on a sec. Every time I press the spacebar, you'll see that there's these small spikes. Now, they are relatively small compared to, say, the rendering, for example, but we can just turn some of the other things off. And if you have a look at this, you'll see that here, for example, it's taking 3.19 milliseconds just to call this one function on 6 objects due to the cost of using find object. But there are ways to work around this. So let's have a look at how you can extend the architecture of your games to not require find object. So one way to do this, and this is the way that I recommend, and there's lots of ways to actually extend this, is to use object registration. This means that when you have an object in your scene or your game of a certain type, and when it becomes enabled, you add it to a manager. And when it's disabled, you remove it from this manager. This means that the manager will keep track of all the relevant objects of a certain type, so that if you want to call a specific function on them, all you do is access the manager and get the references. So instead of searching, all you're doing is returning a list that is already pre-configured. So let's have a look at how you would modify that existing example to do it. So the first thing you'll notice is there is now a tower manager class. And what this is just a mono behavior that will live somewhere in the scene on maybe some aggregated manager game object. But in this case, I've just attached it to the camera. As you can see, it has a static instance, which is a singleton. And then it has a list of towers. Now, when you enable this object, if the singleton is non-existent, you assign it to this. So essentially, there'll be one management object. And every time a tower will become enabled, we'll call the add tower function. And every time a tower is disabled, we'll call the remove tower function. So it's quite simple. All it does is cache the objects. One other thing we have to do is in the tower itself, when a tower is enabled, all we do is we call add tower on the singleton, and when it's disabled, we call remove tower. This actually scales as well and works within the editor, because if you have your scripts execute in edit mode, these functions will also be called. Now, the last step for this is we'll just disable the slow lookup, and you'll see that all we have to do is iterate the towers on the singleton manager. One other nice thing, which is a byproduct of doing this, is you see that we actually avoid an allocation here because we don't need to store a cache list because we're directly accessing it from the singleton itself. And this is actually quite handy because avoiding garbage is a very good thing to do in Unity. So this one last thing with this is you'll want your manager to be initialized before the towers. And you can configure this using the script execution editor in Unity. If you have a look here in the, where is it? Edit, project settings, script execution order. There is this manager where you can assign the order of things that get executed. And you can just change the order, for example, by dragging them up and down. Now that we've made those changes, if we play the game, again, you'll see that every time we call an action, actually, did I enable it? Can't remember if I saved the script. No, I didn't save the script. Now, every time we execute that function, you'll see that there's no spike or a very small spike related to just doing the functionality rather than doing a find object. OK. So moving on from this, as you can see, it's the same example. One thing you can do to extend this is this example's a little bit brittle. It shows the idea without showing a very nice way to implement it into your application. One thing I've seen users do before is write a nice base class that actually tracks all the instances of a type that are active. And this is a relatively robust way to do it. And it's one thing that I would recommend looking into. So you have a base class that extends mono behavior that then you extend your objects off if you wish to use this kind of functionality. OK, so the next thing I'm going to be quickly talking about is better ways to lay out your data in Unity. This is for a few reasons. The first one is going to be related to code reuse, so you can use nice little chunks of code in more areas. And the second one is writing reusable GUI components based off this. So everyone always talks about reuse of code, and for different applications, I think it means slightly different things. And for Unity, what this means is it means you can design your data structures to be used in many different places in your games. It simplifies the drawing and the editor controls, for example, with property drawers. And it actually makes the code a little bit easier to read and understand and maintain when you're using it later on. So what I'm going to show you is an example from the new GUI. I've removed a lot of the cruft code in this, and it just to convey the ideas. So when we started doing a lot of optimization work and data structure layout work on the GUI system, we realized the label class that we'd written actually had a lot of embedded font data. And the font editor class was quite large and overly elaborate. So I'll give you a quick look at what it kind of looked like when we started looking at it. So we had this class here called old label. And what it had inside of it was a lot of embedded data. So there was a font, there was a size, there was a text alignment, a text anchor, and a text clipping setting. Then there was the kind of things that you're actually interested in on your label, so the text and the color. And then finally, there was some effect settings, like, say, for example, a drop shadow or outline. Now, this was all well and good. It worked. But you can sort of see that the data is divided into 3 sections. And the rendering code for this, for the drawer for this, wasn't all that nice either. So where is that? So this is what the old label editor looked like. It was quite rough. You had lots of serialized properties everywhere. You were looking things up on an individual basis, and then your on-inspector GUI was really large, and you had to have special code considerations in there for each section. Now, looking at this, we thought that it made a lot of sense for this data structure to potentially be refactored. So as you can see here, it's divided into sort of sections. So what we did was we refactored this. So we extracted, say, the font-specific settings into a special data structure. We wrote a property drawer for this. And then we were able to also reuse this font data in different locations. Another place we used this, for example, was in the input field. And there's probably others we will use this in before we ship. And we did this in this way. So to start with, we created 2 serializable classes, one for the font settings. Where are we? One for the font settings and one for the effects. Then in the label itself, all we did was reference the font settings and reference the font effects. And because they're public fields and they're serializable, they will serialize correctly. And yeah, there's also a whole bunch of functionality, which is not really important for this example. The next part of this was then rewriting the label editor. Has anyone here used the property drawers that we introduced in Unity 4? Yes? 1, 2, or 3? OK. If you're writing custom editor code, property drawers are internally the de facto way of doing almost everything now. What it does is it allows you to delegate the drawing of your components to like a third-party drawer, and you can specify rules and that kind of thing on it. We gave a talk on this at Malmo at Unite Nordic, and the slides and the videos are actually available online. So you should actually go and have a watch of those if you're not experienced with them. In general, what it does is, you saw earlier that we had a font settings class. If you define a custom property drawer for font settings, it means that any time a font settings is encountered via the Unity inspector editor code, what it will do is it will use this to draw it rather than the default drawing. So in this example, we have the serialized property, which in this case will point to the instance of font settings. You can then find the properties you're interested in and then draw them. So every time a font settings data structure is seen in your code, it'll just use it. And the same things for the effects drawer. And you can also add custom rules here. So for example, you only show the drop shadow value if the drop shadow boolean is selected. So let's have a quick look in the labels. So we have the old label, as you'll see here. And we did actually code the logic for the drop shadow itself. But as you saw before, it was in one on-inspector GUI, and it was quite messy. Whereas with the old label, it still looks the same, except it's rendered in a much more sane and data structure, ease of use way. OK. So once again, I'll reiterate why we recommend using property drawers and why we use them internally. They delegate drawing of your components to a separate class. They're useful for custom controls. And one thing that you can also do is you can actually override default Unity controls. So for example, you could write a custom property drawer for vector3, for example, and anywhere in the code that a vector3 was seen, it would render using your custom control. They're also quite flexible. So you can implicitly link a property drawer to a class. So for example, you saw that we linked it there to the font settings. But they can actually be hooked up on a per field basis via an attribute, which means that if you had a float field that you wanted to be rendered a special way, but only this one float field, you could use an attribute to do that. And you'll actually see that in a little bit when we go on to some data structure validation code. As you saw in those examples, we extensively use serialized properties when working with GUI. There's a very good reason for this. The primary one internally is that it has inbuilt undo and redo support. So by using serialized properties, it means that you don't have to write custom undo and redo code because they handle it for you. It also has inbuilt multi-editing support. Like all of the Unity controls that work through serialized properties do this, which means that you won't have to write crazy hard custom editors. You can just put the right attribute on your class, and if you're using property drawers, it'll just work. It also delegates the drawing, which is something nice. So you have your inspector code separated from your control drawing code. This is all very good, though, when it comes to drawing custom editors. But what about the data validation on the fields in your classes? So using serialized properties and property drawers, you can actually validate your data on the UI level. You can do this via property drawers that do the validation, or by manual validation. And let's have a quick look at how that would work. So I'll open up our validation example. So here we have a class, and it is just simply a script called validateMe01. And I will open it here. And what it has is it's just two fields. It has a public float called myFloatValue, and it has a public string called myString. Now, as you can see in the comments above the fields, we actually want to do some validation. So for the float field, we actually want to only allow the valid range to be between 0 and 3.5. And for the string, we want it to contain less than 15 characters. So for this first example, as you can see, we don't actually have any validation occurring. So when I go back here, you'll be able to see that this field can go up and down outside of the ranges we want. And we can also enter much more than 15 characters, and it just allows it. So the first form of validation we're going to be using on this is via property drawers. If we have a look here, if we have a look here, you'll see that the validateMe02 class actually uses a property drawer on a per attribute basis for the float called range, and a string clamp property drawer for the string. If we have a look at these property drawers, you'll see that they are very much the same. We'll go on to them in a moment, as the ones for, here we are. So they're very much the same as the ones we saw before. So we have a custom property drawer called range attribute, an extends property drawer. And what we do is we draw a slider for this property, and we limit the range to the value that the drawer was constructed with. You'll actually see here that we actually have the attributes here living on the runtime side, but the drawer is living on the editor side. Now, the reason that the attributes live on the runtime side is because otherwise you would need to mark up every property drawer you use with a if editor GUI or if Unity editor, and we didn't really want to do that. So the actual attributes themselves are very lightweight. All they are is two fields, or however many fields your drawer takes. But the actual logic and validation is done with the editor side code. So let's just make this come back here. So let's have a look at the range attribute, or the range drawer, in a little bit more detail. So what you get with your property when it's time to draw is there's a few things that live in the base class of the property drawer. You get the attribute, which is the referenced attribute on the field, and you get the property, which is the field you're trying to draw. So the first thing we can do is we can cast the attribute to the range attribute, and we know it's the right one because this is just by definition based on the type that's passed in. And then all we can do is simply just draw a float slider if it's a float field, or an int slider if it's an int field. Otherwise, we just draw a label field saying use range with float or int. Quite simple. And a similar thing for the string clamp drawer, where we just ensure that the range of the drawing is, or the range of the string that's entered is between 0 and 15. Now, if we quickly jump back to here and we open up the second example, you'll see that the slider now goes between 0 and 3.5. And if you enter text that's longer than 15, it'll actually clamp it back down to 15 characters. But this is a little bit brittle, because there are multiple ways your data can be edited, and it's not always via the UI. So let's have a look at some ways and some better data structure patterns of data structure validation patterns in Unity. All serialized objects in Unity have a callback called onValidate. Now, this is an editor-only callback that is used, which you can use for data validation, and it's called whenever a property is changed. So if we open up the third example here, you'll see that we have the float value and the string value like we had before. Now, we wrap this in a nice if Unity editor block now, and then we clamp them when they are in the onValidate. And this ensures that the data stays in this range. One thing to note is we've actually removed the property drawers here, so that if we select the third one, you'll notice that the ranges get validated as expected, like so, but we don't actually have nice drawers. So that leads to the next point. If we want to use robust data validation, it actually makes sense to use both the property drawer for the GUI and the validation for ensuring the data integrity. But this also falls a little bit apart in the runtime, because onValidate doesn't get called in the runtime. You can't be sure that your data is going to maintain the rules that you've set out for it. So the next step in this is extending the model so that your classes have getter and setter properties and also validation within these. Then have the onValidate function call the setter for these fields. This means you only have to write your validation code once, and it will work in both the editor and the runtime. So let's have a look. It's actually the fifth example for this. OK, so now you actually get quite a bit more boilerplate code, but a very robust data structure class that will work well in the editor and the runtime. As you can see at the top, I've just defined some consts so we don't have to manually enter fields in lots of places. And we have a private field called myFloatValue, which has a range between the minimum and the maximum. And we have the string with the string clamp, as we saw earlier. Now, for the data validation, it's actually done in the properties, or the public properties. So when someone tries to set the float value, we clamp it between the minimum value and the maximum value. And then we only set it if the data is actually considered changed. And the same with the string. And the final point on this is so that the validation occurs correctly in the editor if you edit the data via serialized properties, is all we do is we set the public value to the private value, which will mean that if the value gets changed, it'll also be validated. If it's not immediately obvious why we need to do that, it's possible to edit the data in your class without going through the serialized property system. So if we look at validate me02, you saw that we had the UI validation. But if we click here and switch to the debug inspector, there's no validation being called. So I could enter 65 here, and Unity would think it's OK. And then if I jump back to here, it would actually be 65, which is not what we want. So yes, that is, in my mind, the correct way to do top-to-bottom data validation on your data structures in Unity. And I think it's quite robust. So this is roughly similar, or it follows a similar methodology to the MVC model. We separate the data representation and the data validation from the user interaction. We do provide ranges and limits and data validation on the UI elements, but we don't make this the only way the data is validated. We consider this more a way to sanitize the input, whereas the data validation actually takes place underneath, internally in the data structure. But there's a few little pitfalls that can come from doing this, and we need to make sure that we don't fall into them. One of the things we try very hard to do in Unity is make sure that, say, for example, when you open a scene or when you click on an object in the scene, that the inspector will only actually modify the data in your object if a user action occurs. Because what happens is, if you don't do this, just by selecting an object, you can modify the scene, and that doesn't make sense to us. So for example, editors should only change their information on their own instance, and not on others as well, because otherwise they could mark the scene dirty for no apparent reason, especially if they point to something like a prefab. So a real-world example of this is, consider a data structure that has two modes. One is calculated from state. Essentially, this means, let's say you have, an example of this is like a label in a font rendering system. And if you have the model allow the bounds of the font to be changed based on what the text is, that means that if you modified like a metadata file or something like this and changed the text, that potentially just by loading the scene, you would modify the data in the scene, which is incorrect. The other model is if the data is user-controlled, which is you would then expect the data to change. OK, so let's have a quick look at how this would work. So in the Pitfall example, OK, so here we have the first class, and we have just a enum called DataState, and this this tells the inspector or the data structure if it's modified by the user or by the system. Then we have two values, and we actually have some similar data validation to what we saw earlier. Now, in the onEnable of this class, we set the value to be a complex value based on something. In this case, it's just a random range, but this could be some internal data that modifies the fields. Now, the problem with this is that when you have your data structure, simply by calling the onEnable function, got to set to user modified. Simply by calling the onEnable function, you'll modify the data. Now, this may be what you want for the data structure. You may want the engine to control what the data is. What you don't want to do is touch the serialized data. You just want it to be, say, a runtime artifact, not a serialized artifact. So the way to fix this is to do something a little bit, hang on, OK, yeah. The way to do this is do something a little bit more complex. We have the serialized value for the data, and then we have a non-serialized value, which is essentially the local cache that you work with. By doing this, you'll actually make your data structures slightly larger, but it also means that it works correctly with the undo and redo models in Unity. So what happens is when you set a value, or when we call the set value on this, if the data is allowed to be user modifiable, we consider this to be an action that is being taken place to modify the data, and we actually change the serialized value. Otherwise, we just set the value, and we also then set the value in the cache. In the onEnable function, we just use a little property setting trick here to set the right value. And this means that we essentially have a shadowed state. So if you're in user modified mode, you will always be editing the serialized data, whereas if you're in the engine modification mode, you will not be touching the serialized data. And this is something that's very important to do. And if you ever have some custom editors or custom data structures, and you just open an inspector and see the scene get marked as dirty, you're probably not following this rule quite right. Okay, so let's move on to something a little bit more exciting. And we're going to be talking about ways to use performance and memory debugging in Unity, using both the built-in tools and some third-party tools. So one thing we do is we highly recommend that if you've got a Unity Pro license, that you use the built-in profiler and check your your GC tracked allocations per frame, and try and keep this as close to 0 as possible. Sometimes it's not feasible to do this for various reasons, but a lot of the games we see can do a lot better when it comes to managing their own allocations. So how can we do this? Let's have a quick look. Have you heard of the Stealth Learn project that the Unity Learn team did? Because what we're going to do is we're just going to have a quick look at that. Now, one important thing when you're doing profiling is it's actually not a good idea to profile in the editor. You can get a rough idea of what's happening, but there is a lot of editor overhead and editor data that is still tracked by our memory allocation and tracking systems. So the best thing to do is actually attach the debugger or the performance analyzer to a separate application, which you've built with debugging enabled. So what we're going to do is we're just going to boot a copy of Stealth I built earlier. And here we go. It just takes a minute to boot. And then we are going to attach this as the active profiler. Now what you'll see here is you'll actually see essentially what's happening as the game runs. And there's lots of little things, like there's the green for the rendering, the blue for the script performance, and there's a little legend here on the left that shows you what everything is. What we're looking at now for the mono memory debugging isn't this. That's not the important thing. What we actually want to do is we just want to run around the game for a little bit and make a few things happen. So there's going to be a robot here or something, I think. Here we go. And we're just going to quickly jump back to Unity and just pause, essentially, what's happening. And as you can see, you can actually sort these columns based on like highest to lowest or lowest to highest and different things. So use the time to essentially look at the CPU performance and how long things are taking. So as you can see, in this scene, the rendering is actually taking quite a lot of time, specifically the culling. And you could look into that. But what we're going to do is look at the garbage collection, or the GC alloc. What this column tells you is it tells you the amount of memory that's being allocated in this sample for each function call on the left here. So as you can see here, there's a script which does done camera movement, fixed update. And if you have a look at this, it's allocating 420 bytes. And every time this script is called, it's potentially, it's allocating a number of bytes every time. What this means is that it's actually quite bad because you're generating garbage that the garbage collector has to handle. There are many ways to get around this. You can actually cache this field in your class so you don't have to allocate it every time. You can use a list that grows slowly, but you track the memory itself. But what you don't want to do is you don't want to have something that is new each time. So let's have a look at this. Just bear with me 1 second. I'll actually quit this as well. So if you have a look here, the script is done camera movement, fixed update, which we actually have here already, because I was looking at it earlier. As you can see, there's actually a lot of cache variables here that are being used. Like there's the standard position, there's the above position, and there's this. And arrays are probably the worst thing for this. Every time this function is called, it's actually allocating a fixed vector of checkpoints. And this data is going to be most likely hit by the GC And there's also functions here that may do more allocations. The thing to do is make these functions allocate 0 bytes or 0 kilobytes per frame, and either by caching the values or not, and you'll actually hit the GCLS, and you'll have less hitches in your game. Okay, so let's have a look. Where is my slides? Here we are. Yes. So always try and keep these allocations as close to 0 as possible. It's not always possible, but you should do the best you can. Okay, so some examples we see a lot of is allocations in a function every frame. I was looking at an example earlier today or yesterday where I saw someone was allocating in one function 1 kilobyte a frame. So that means every 1,000 frames of their game, they were allocating 1 megabyte of garbage roughly. And that's going to be very slow and very hard for the GC to track. What I recommend, like I said earlier, is use the profiler frequently, attach it remotely to your application, and really don't wait till the end of your project to do this. I try and do this once every week or 2 weeks on a lot of the code I work on, because sometimes it can be too late. Like you're very much built to a certain data structure or data design, and if you don't catch it when you're designing the system, it can be too late. So let's have a look at the next one, which is looking at the runtime memory state. This is actually very important if you're looking at trying to target a low memory device like the iOS devices or the Android devices, but it's also very important if you're on a PC as well. So once again, we'll load up the stealth demo that we were looking at before. And we'll just clear this up. Now, you can actually, if you click on the memory tab, you'll see that you get an okay overview of what's going on in the runtime, but it's nothing super advanced. It's just a little bit of information. But if you switch here to the detailed view, you can take a snapshot of what's happening in the runtime at that time. And it actually gives you a breakdown of the memory usage. So as you can see here, there's 159 megabytes of assets loaded at this stage. These are assets that are either referenced by the scene that's currently running, or assets that are located in a resources folder in the project that are always loaded. So let's have a look, and you can further break this down. So you've got textures, meshes, audio clips, shaders, etc. And you can see where roughly all of the memory in your game is with regards to assets. As you can see here, for a game like this, like 107 megabytes of texture usages seems a little bit much. So let's have a look at what could potentially be the problem, or why the usage is so high. And as you look through here, you can see that some of the textures are like 1.3 megabytes, might be a bit big, might not be. But at the very top, you'll see that we have a 21 megabyte texture. Now, the moment I see something like this, I instantly think that there's something wrong. Either the texture is too high resolution, or compression's disabled, or something like this. So let's have a quick look in the project to see what how this texture is configured. Oops, prop bus. What is it called, sorry? Body underscore. So if you have a look at this texture, you'll actually see that it's actually in true color and not compressed. So if we change this, we can obviously reduce the memory usage of this texture. It's very important to do this as you go through your project. And sometimes you will have to make tough decisions. So for example, you may choose to not have such high resolution textures in your game. You may have lower resolution textures and you will lose a bit of quality, but at the same time you'll save memory. And this is very important if you're trying to hit older models or older devices where there's less RAM available. So to have a bit more of a look at this memory analysis, where'd it go? It went away. I'll just bring that back up again. There's a few other areas in there that are quite interesting as well. So the assets track the raw asset types that you have, say your textures and your sounds and things that are referenced by the game. Not saved assets are things that you create that do not serialize between scenes. So for example, in this case, it's things like render textures. So here we have a 32 megabyte off-screen render texture. That's quite a lot of memory, so you might want to look at why that's happening, for example. And you also have a little thing on the right, which is quite nice. So for example, you can see what materials, for example, reference your textures and how many references there are to it. After not saved, there's things like other, and others track things like the size of your executable and your DLLs. One thing you can notice is if you're on an iOS, you can use this to check the size difference between a stripped and a non-stripped build. And if you have a debug build, you can also see the profiler overhead because there's data embedded in the application for that, as well as various other pieces of application. The next one is scene memory. This is stuff that's stored, or things that are stored in the scene that isn't part of the asset itself. So these meshes might be combined. Yeah, they're combined static batching meshes or dynamic batching meshes. Copies of the animated components that are required for local state tracking, and different things like this. The best thing to do is to profile your application using the memory profiler and see what's big and what's not big. A lot of the time you can see things that you would expect to not be there and then fix them quite simply. And this is one of the first things I do when I look at a third-party project. I check to see exactly what's happening with regards to the memory status, especially if people are complaining that their application doesn't fit on their device. Okay, so once again, use the profiler frequently, attach it remotely due to the editor adding overhead. Don't wait till the end of your project to do this. An extra point is always name your objects. For example, if you create a new object, and you'll actually see this here because it's not quite nice, you'll see that there's the not saved render textures. These are just been temporarily allocated, and they're called things like temp buffer 7. That's really not useful when you're trying to debug a project. It's much better that when you create a render texture, you give the game object a name. And by doing this, you'll actually see that pop up in the profiler. So you'll see, oh, it's my off-screen buffer 3 that handles the weather effects in my game, and you can immediately know what is happening with your memory allocations. Many of the issues we get from the users are actually quite self-evident and diagnosable once going through the performance and memory profiles that come with Unity. Yes. So the next point I'm going to go across is graphics debugging. And that is, there's a lot of questions we get that are like, so why is my game running slowly? And there's a few ways to figure out why this is. And there's two sides to this. There's the CPU side rendering cost, which is the calculations we do to actually figure out what needs to be rendered and all the shader state binding and that kind of thing. But then there's also the time it takes and the things that need to be rendered on the graphics card and on the driver side of the graphics rendering. Most of the times, the things we see that really kill projects are things like overdraw and draw call count. But let's start by having a quick look, once again, at the stealth project. And we're going to have a look at the CPU analysis here. Now, as you can see, with the rendering, it's rendering at 15 FPS. That's because I'm running on a VM at the moment, so it's not very nice at all. But you'll see that at the top of the, hang on, we'll arrange this by this. Yes, so as you can see here, the GUI is taking a nice 32 milliseconds to render. Now, as you probably know, we're shipping a new GUI as soon as we can, and this is one of the reasons. Like, the old GUI is horrendously slow. So I hope you look forward to it as much as I do. But if you have a look through this, you can actually see the camera render. Now, this is essentially where all of the rendering time is spent for Unity on the CPU side. And things that this function does is it calculates what needs to be rendered, how it needs to be rendered, shader bindings and the like. So you can see here for the opaque geometry, and then it does pre-pass lighting, so it's using a deferred rendering. And you can see where all the calculation time is spent. It's actually good to have a look on your project to see if deferred or forward is faster for calculation, and what things can be batched together or not batched together. A lot of the time, you might not be able to do so much about the camera rendering time, apart from render less or be smarter about what you render in your application. But that's the CPU side. let's have a look at the GPU side. Now, there are a few tools that you can use for graphics debugging on the GPU side, and they actually work quite well with Unity. The tools I normally use are Pix for Windows, which is an older style debugger, Intel GPA, and Visual Studio 2012 graphics debugging. When you use these tools, it's important to remember to build your standalone player with the developer mode enabled, because otherwise you won't get some nice symbols we insert in the outputted result. So each one of these tools that I mentioned is better for figuring out different things. So Pix for Windows is the oldest. It has DirectX 9 and DirectX 11 support. And it's good for figuring out your texture usage, your shaders, your draw calls, and exactly what's being rendered. Intel GPA is a graphics debugger provided by Intel, and it has DirectX 9 and 11 support, and it has much better things for draw call timing, so you can figure out exactly how long things are taking to render and texture usage and that kind of thing. And I find personally it's the usability and the front end is a little bit difficult to use to start with, but once you understand it, you get a lot of good information. Now, the third one is Visual Studio 2000 graphics debugging tool. It's DirectX only 11, and it's essentially the new Pix. As far as I'm aware, Microsoft aren't maintaining or upgrading the new Pix, and they're shipping it as part of their developer chain, tool chain in Visual Studio. And it's actually quite nice, except it doesn't have DirectX 9 support. And unfortunately for OS X, there's not much at all. There's a few OpenGL tools, but I've found them very hard to use, and you get not much compared to what you can with out of the box for the Windows tools. So unfortunately, I do most of my graphics debugging on Windows. Luckily, a lot of the things you see, or most of the things you see, are applicable to all platforms, because there'll be higher level optimizations you're doing, not, say, driver level optimizations. Graphics debugging tends to be slightly more sane on DirectX 11 applications. This is due to better drivers and APIs, and things are a lot more tidy. You can build your Unity game in DirectX 11, or you can actually force any Unity 4.0 Plus game to run in DirectX 11 using the force DX11 flags. If you don't have a DirectX 11 game, or you have some custom shaders that aren't DirectX 11 calculated, they may not show up. They'll just be purple. This isn't ideal, but you can get a lot of debugging done still if you don't have all of the shaders working. Just some of your timings might be off because your shaders are not going to be as complex as they could be. What we're going to do is we're going to have a look at the Stealth Learn project just quickly. We're going to go through this very quickly because we're running out of time. And we were originally going to look at this using the Visual Studio 2012 graphics debugger, but it doesn't run in the VM, so we're just going to use the old Pix for Windows. So let's have a quick look. So as you can see here, I've just got it booted already. You give it a target application, which in this case is the build of Stealth, and then you have a key combination. When you press it, it will take a screen capture or a graphics capture. So we're just going to do this quite quickly. You get a little thing in the top left corner so you know it's actually running. And here we go. So I'll just do a capture now, quite quickly. And after you quit, you can do multiple captures, and they'll actually show up in the timeline here. And you get like a little view saying the frame that was captured, how long it took. After you do a capture, you shouldn't really trust this because it's the time the capture took, not the time the actual render took. But then you can break this down and have a look at every draw call, every state change, and everything that happened in your DirectX 11 render, or DirectX render call, I should say. So if you have a look here, you'll see that we've actually inserted some things. So you've got the image effects, the GUI layer, the drawing, so you can see exactly what was rendered and when. So if we open this tab, it will actually show you what was rendered at each stage. So if we start here, you'll see that that's all the opaque geometry that was rendered, but we can drill down further. And where are we? And say, this was the result rendering of the geometry pass for the G buffer. This was the result of the lighting pass for the G buffer. And this was the result of the rendering for the combined, the lighting and the geometry. And then further than this, though, we can actually go down and have a look at the rendering of each light into the gbuffer. As you can see, these lights aren't doing much, but these lights are. So these lights here that aren't doing much at the start, it's potentially they're not needed in the scene. And you can see that, oh, maybe I should look at these lights and optimize them out of my game so they don't actually take time rendering and that kind of thing. We use this a lot to essentially figure out what's being rendering and and if the results are correct. You can also, if you expand these, you can also check the states and see what textures are bound, but I won't go through that now. If you want to have a look at the performance analysis on Windows, the best thing to use is Intel GPA. Because you get a nice little graph of how long it expects each red draw call to take. And you can select a draw call, see all the textures that were rendered, the shader that was used, and the mesh that was rendered at the time. But that also didn't work on the VM, unfortunately, so I couldn't show you. OK, so moving on, I'm just going to give you a quick overview of a new feature we have coming in 4.x that's shipping with a new GUI. And that is the Unity event system. So one thing that we've had a lot of requests for is persistent callbacks. And for us, what this means is the ability to configure a callback in the editor at the time you build your game, and then have it execute in the runtime based on a certain event. So you can do this with delegates, essentially, but you need to write a script to hook them up. They don't save, they don't serialize, and that kind of thing. And they also have some problems with regards to how they're referenced. So if you have an object that is being pointed to by one of your delegates, if you still hold a reference to that delegate somewhere, even if it's the only thing holding a reference, that object will never be GC'd. And in a game, that's not really desirable. Because if you have, say, a game object that you delete, yet there is a delegate somewhere holding a reference to it, you actually want that delegate to probably not be called because the game object's gone away. So we solved this problem by using the weak referencing system on the persistent delegates, which means that if a game object goes away, we just simply won't call the function on it, and the reference won't be considered by the GC to be a real reference, and it will still be garbage collected. So how do our Unity events work? They're generic-based, and there are a variety of types supported out of the box, and you can actually write your own and extend the system further. But we provide a default of 0 arguments to 4 arguments, because we considered that that would probably be enough for most situations when it came to event callbacks. And they're simple to use, and you can extend the Unity event with your desired type arguments. So as you can see here, this is an example from the new GUI system. So we have a serializable event that extends Unity event. And in the generic arguments there, you can see that the type is button. This means that whenever you invoke this function or this event, it expects the button to be the argument, a button instance to be the argument on the invoke. We actually, unfortunately, needed to write a new class for this that extends the base one. And this is because Unity doesn't support generic serialization very well out of the box. And you need a concrete instance. And the serialization system considers it enough that you have a class that extends the generic instance so that it's OK. To call a Unity event, it's quite simple. All you do is call the invoke with the required arguments. And in this case, the on-click event lives in a button, so we're just passing that through. You can add a persistent event in lots of ways, or in 2 ways, I should say. That's not very many lots. You can add a listener by using just the function call. And if you're in an editor script, it will be saved and persist with your game when you build it or play it, for example. Or you can actually use a little GUI component we wrote. As a note, this GUI component actually uses property drawers, so we're using them internally as well. As you can see here on the left-hand side, you configure the game object you want to have the callback on, and then based on the type of delegate, or based on the type of Unity event it is, we'll populate the drop-down on the right with all of the valid functions on all of the scripts on the component, on the game object. So it's actually quite nice, and it'll only show the things that are valid. You can add a runtime event as well, and this is something if you want to hook something. This is, for example, if you would like to hook something up at runtime, and all you have to do is call add listener. Runtime events are not quite the same as persistent events. They follow many of the same rules, except they won't ever be serialized. it's just so you can use the one invoke without having to use a combination of C# delegates and Unity delegates. It's a nice helper. And Unity action is actually based on a delegate type. And we just need this because the delegate type holds a lot of nice information and syntactic sugar for the construction of these. So what kind of listeners can be hooked up to Unity events? Persistent events can only reference components. And that's because we needed something that is actually persisted, whereas runtime events can reference anything. If your listener is a component, it will only actually be executed if the component is considered active. So that means that it's quite nice. So you don't have to worry about checking if your component is enabled or disabled, for example, when you call a delegate or an event. Okay, I've covered a few different topics, and I was wondering if there's any questions. I think we probably have 5 minutes or so, maybe a bit less. We might be able to stretch it out. But if you have a question, feel free to just go to the microphone there. Cool. Feel free, if you have any questions, to come up and grab me. I'll probably be around for half an hour longer or so, maybe, just walking around. But after that, it's probably your last chance.